Okay, so in the previous lesson, what we studied was that if we do have magnets, permanent magnets, and we place a conductor between them, then be that the current out of the page or into the page, it will experience a force that is upwards or downwards, basically perpendicular to the magnetic field direction. So this is my magnetic field direction, and that is the direction of my force. So it will experience a force perpendicular to that. And the reason, of course, being that for Fleming's left-hand rule, all three axes are perpendicular to each other. So this is 90, this is 90, and this is also 90, right? Okay, this is what we have already done. Now, in the last lesson, what we did was that we did the same idea in a three-dimensional perspective. Today, we're going to carry that concept towards the DC motor. That effect that we did yesterday was known as the motor effect, and we learned how to use the Fleming's left-hand rule. Now we're going to apply the Fleming's left-hand rule in this situation, that is the DC motor, to understand it fully. Okay, so we must have the Fleming's left-hand rule in mind, and then from that point onwards, we can start working with it. So this is what the DC motor looks like, and to complete the rest of the diagram, is just cropped out, that's all. So just imagine that this is the battery, and this is just a switch. Okay, although they connected a variable resistor over there to control the speed of the motor, but that's not the part of the discussion right now. We need to understand how it works, we need to understand how it rotates and moves, and for that we are looking at its construction. We will also look at a video animation to fully understand it, right? Okay, so the examiner will not tell you, be advised that he will not tell you that what is the direction of the current. Although over here we can see that these small arrows are already made, but that is for the discussion purpose. But what he's going to do is going to give you the signs of the battery. He will tell you that this is positive and this is negative. And of course, in physics, we are following the direction of the conventional current always, as always. So this should be my indication that what will be the direction of current. Now, the parts that are labeled X and Y, these parts are not known as the carbon brushes. We are using carbon because it is a good conductor in terms of graphite configuration, right? You must have done this, or you will eventually do this in chemistry, O levels and A levels, that carbon in a graphite configuration is a good conductor. There is one electron that is left between the layers, so that helps with the conduction of electricity. Not only that, but those layers can slide off one another, and eventually this also acts as a dry lubricant. So carbon brush is not only a good conductor, it's not only a good conductor, but it is also acting as a dry lubricant. It has very minimal friction. And why do we need minimal friction is that the reason for that would be that when the current eventually does pass from this conductor, that is AB, this side, and CD, this side, the thing that we did yesterday, that if a current through the magnetic field or if a current carrying conductor is placed in a magnetic field, it will experience a force. So over here we do have two conductors carrying current in the presence of an external magnetic field, so they will also experience a force. So let's figure this out later, but for the sake of example, let's say that the direction of the force on side AB is downwards and the direction on CD is upwards. They will always be acting in a pair of a couple. If one side is experiencing force downwards, the other one will experience upwards. Why? Because the current is completing one loop. So if this current is moving in this way and this current is moving downwards or out of the page, then of course if you apply the Fleming's left-hand rule on AB, that will give us one answer. And if you apply the same rule in CD, that will give me the opposite answer. Just because the direction of the current is changing, the direction of the force will also change. If you remember, we discussed this yesterday, that we are not changing the poles that are placed on the outside. The north and south were over there. But if, for the sake of understanding, we talk about the conductor that is the dot conductor, the current that is coming out of the page experiences a force that is upwards. And the conductor that has a cross current experiences a force downwards. Again, you are supposed to use the Fleming's left-hand rule to figure this direction out, right? So the same conductor with same dimensions, same current, placed in the same magnetic field. Just because the current is different, they will experience different forces, or the force in the different direction. Similar thing happens over here. Now, when these forces do exist, when they do get applied on this coil, the coil starts to rotate in the direction that is highlighted over here, as we can see that very clearly. Now, to give you a real life example, where do we see that in real life? You can see, or you can look at the ceiling fan. It is rotating. Although the ceiling fan is an AC machine, it's an AC motor, but for the sake of discussion, I can take the real life example of the motion of an AC motor to justify with a DC motor. Okay, so since we look at this rotation or we see this rotation, the coil will start rotating, and if you have connected some mechanical object on the other end, let's say, and in the case of a fan, we have attached blades to it so that it rotates and gives us with the airflow or gives us airflow. So those will also start rotating, right? So the carbon brushes are required over here to maintain a good contact, not only a good contact, but we want it to produce minimum friction, right? So when these split rings, this one, the circular part, let me highlight that again. These circular parts are actually connected with these wires. We will look at the three-dimensional diagram. It will make it more clear. So when this coil rotates, these are also rotating with it. What we want is that when they do rotate above or in contact or while in contact with the carbon brush, we want it to have minimum effect on this rotation. We want it to have minimum effect. So it has to be a dry lubricant, or it has to have minimum friction, and it has to be a good conductor. So the best choice was the carbon material in a graphite configuration. The other configuration for carbon is diamond, and which is one of the hardest substances known to man, and it is not a good electrical conductor. So just one step back, we have graphite, and you will see this in chemistry that graphite under extreme pressure the eventually does become diamond. And the south pole is on the left side, as opposed to the directions that we have done in class. I always draw the north pole on the left side and the south on the right side. There is no compulsion with that. You just need to know how to implement the Fleming's left hand rule. It doesn't matter. Now, notice that the examiner will not give you the direction of current. You have to figure this out on your own. And I can see that this terminal is the positive terminal and this is the negative terminal, right? So I can say that this will be the direction of the current, leaving the positive terminal and then coming back to the negative terminal. And if I continue this through the carbon brush, this black part or the gray part is the carbon brush. So if I continue down this road, I encounter this split ring. We have deliberately cut this into two halves, and what's the reason for that? We'll explore that later. So the current reaches the carbon brush. Carbon is a good conductor. It then encounters a split ring, that is the curved part. It is made out of copper or the same metal that we use in this location. So again, it's a good conductor. So the current eventually goes through this coil over here and then goes to this side, completes its loop, comes back down again through this coil, goes back and then to the battery. So in this way, the current is going to complete its loop. Do we understand the flow of current through the coil? Right? Now, if we go back to the perspective that we did yesterday, it becomes a bit interesting. So if I look at this conductor, if you were standing at this point, the current is moving in this direction. So to your eyes or to your perspective, this is the south pole in two dimensions. This is the north pole. The conductor looks like that the current is moving away from you. Is that right? Do we understand this? Right? And if you were standing at this point, just for the sake of understanding, the current is moving towards your perspective, right? So this diagram, or on this side, this would become south and north, and the conductor carrying current in the dot configuration, right? So if I implement the Fleming's left hand rule either in three dimensions in this diagram or either in two dimensions in this diagram, for the sake of understanding, both will give you the correct answer. Now let's try to see, or even if you go a bit deeper for your own proper understanding, then you'll have to do it this way, that the magnetic field external one is the north to south. Do we remember this analysis of magnetic fields? Right? So then we'll have to go towards that side. Then we'll have to go towards that route. But then we established over there in the last lesson that it is inconvenient and takes a lot of time. Although conceptually it's very empowering, but it takes a lot of time and it's not feasible for us. So what we created for the convenience is the Fleming's left hand rule. So I just drawn this example or I've drawn them for your understanding or for your two-dimensional perspective, but we are actually going to implement the rule in this three-dimensional situation. So if I look at it from this perspective, I'll have to use my left hand again. I'll have to use my left hand. So my first finger should point towards the left. Now, what I would recommend is if you want to implement this more easily, so this is where you're sitting right now, right? I'm looking at you from the back, right? So this is your head, right? And you're looking away towards the screen. So this is your left side and this is your right side. Do we understand how we're looking at you, right? So extend your left arm outwards as far as you can go in a straight manner. And then if you point towards the left wall with your first finger, you would have successfully implemented the first rule that we have to move from north to south, or we actually point towards south. Do we understand what we've done? Right? So now you're pointing towards the left side with your first finger of the left hand, right? And if you notice, now open up the second finger. Naturally, wherever it opens, you will see the second finger automatically opens like this, pointing into the page. Is that so? Right? If you have extended your arm to the left side, right? So your finger automatically opens up in the direction of the current that is in this conductor. And since we've now completed the first and second step, we can successfully open up the thumb automatically. And you will see that if you open up the thumb in this condition automatically, in convenient position, not changing the hand, you will see that the thumb opens up in the upwards direction. Is that so? Right? So your hand would end up looking like this, that this is your thumb. Sorry. So this is your thumb direction upwards. This is your first finger. And your second finger is pointing into the screen somewhat like this. This is your left hand, or this is what it should look like. Do we understand this? Right? So keeping this in mind, what I'm going to do, I'm going to show that the force exerted on this conductor is going to be upwards. Right? And if I move towards the right side, I will naturally always find this force to be the opposite of the first one or the left one. Or if you found the force for the second one first, then it will be the opposite to the first one. So they act in a couple fashion so that it can complete its one rotation. But anyways, for the sake of practice, we're going to find this out nonetheless. So again, extend your arm to the left side as you did before. And now just rotate your wrist in such a way that the current is pointing outwards. So what you should look at with your hand is that you're pointing again, extending to the extreme left side, your left arm, right? Pointing to the left side because we are pointing to the South Pole. This is what we have to do. And now you have to rotate your wrist in such a way that the second finger now points outwards. So you will see that if this is your finger, first finger, now the second finger would be pointing outwards in this fashion. So this is my first finger, this is my second finger. And if you open up the thumb naturally in this configuration, your thumb will open up downwards. See if you can do that. What we can say is that the force on this side of the conductor is being exerted downwards, right? So again, this will help us complete one rotation. But this brings us to the next part of the lesson, and that is that if that happens, then what's going to happen with this distinct cut that we have at the center? What's going to happen with that? So I'm going to clear this out since we understand the first configuration. Now, just remember that after this rotation, we will see that, just a moment, we will see that the rotation will continue because if I look at the fan keeps rotating in just one direction, right? So in order for this rotation to be singular or to be in just one direction, I have to make sure that there is a cut at the center. Now let's discuss what this brings to the system and what implications it has. So let's play this animation for now and see what happens. Okay, so observe that the direction we figured out on that side was upwards and on this side was downwards. So it does rotate in this direction, right? Do we see the rotation of the motor? Yes. Now let's try to go back over here a bit. Now just imagine that this side that we were discussing or we started the discussion with, now that side previously was on this point, the coil itself, and now it has moved upwards and this has moved downwards. Is that so? Right? So similarly, if I take just a few steps forward, so I can say that my left side is on the right side and my right side is on the left side. Is that so? Right? So I have exchanged positions, and luckily now what one thing you'll have to observe as well, I'm going to clear this out. Observe one more thing. Observe what happens with the split rings. They were solidly connected with their own respective coil. They have also changed their location, but try to notice that if you see that happening in this location. So I'm going to do that again. Do you see that they also change their location along with the side that they are permanently connected to? Do we see that? Right? Okay, so because of this, now just imagine what has happened is that this carbon brush broke its connection with this split ring when it completed its rotation, and now wherever we started the question from, that carbon brush is stationary on its own position. But the carbon brush's split ring, or the pair it had at the very beginning of the question, that is on this side, and this carbon brush's pair of the split ring is on this side right now. Do we understand this? Right? They exchange their positions, right? Now let's analyze over here the situation again. So what I see is that the current is still moving in this direction and over here in this direction and over here coming back to the circuit again. So if you notice the direction of the current in the wire or in the conductor, that is right now for the sake of discussion closer to the south pole, it is always away from us. Is that so? If we were standing at this point, just a moment. And the direction of the current, no matter it was the left coil or it was the right coil, wherever they were, whenever this conductor encounters the north pole or whenever it comes closer to the north pole, it is experiencing a direction of current that is downwards. So does it matter where the position of the DC motor is in its lifetime? The always, for this configuration, of course, if I had changed the position of the north and south, then I would have done a different discussion. But I realized that it doesn't matter that whatever conductor comes close to the south pole, just for the sake of reference, it's not going to happen every time. Because if I reverse the batteries, this is negative and this is positive, then this current would always be downwards, not upwards, right? So just for the sake of this configuration, I realized that no matter this conductor comes to south pole or this conductor goes to north pole, whatever side of the coil encounters the south pole is experiencing a current that is away from us into the page. And whatever side of the conductor comes to the north pole, it encounters the current direction that is out of the page or coming towards our perspective. And this is why it ends up experiencing the same force no matter what side it comes from. So this side always experiences an upward force, this side always experiences a downward force. And who has done this job? Who has helped us to achieve this task? That are, or those parts are the split rings. They actually physically detach themselves from this carbon brush and then connect themselves to the next one so that the direction of the current can change. Now, what do we mean by that? You see, if I were to label this side of the conductor, it was experiencing the current upwards, previous lifetime. But if this conductor comes after rotation to this side, then the same conductor experiences the current downwards. Who did that? The carbon brush detachment with the split ring did that. Now let's try to analyze the situation one more time. So this is where they are right now. Okay. Now let's try to move them step by step physically to the other side and see what do they do. So it physically detached itself from the first carbon brush and now made a contact with the second one. So now see this wire or the wire that was previously at this point is now on this location. Do we understand this idea? Right? Is that acceptable? Hmm. Okay. So previously, when it was over here, it experienced a current in the upwards direction. Now it's here, it is experiencing a current in the downwards direction. because it is connected to the negative side, so the current is going to complete its loop and then go over here. So what happened with that single side of the conductor? When it was closer to south, it experienced a current upwards. When it's closer to north, it experienced a current downwards. Who did that? The split rings detachment did that. Because when it was connected with the first carbon rush, it experienced a current coming towards the coil. When it connected to the second carbon rush, now it is experiencing a current moving away from the coil. Do we understand that this change in direction of current is actually done or helped by the split ring because it has a cut between it, or it has a cut at the center. So it actually detaches itself from the first carbon rush and then connects itself to the second one. That's how it's working. Do we understand this idea? We're going to look at the factors affecting the DC motor, the motor effect. And they are very simple or pretty simple. So if I want to increase the speed, or in short, the turning effect of this DC motor, then what am I supposed to do? So what changes I can do? I can increase the current through the coil. It will produce a stronger magnetic effect, hence producing stronger rotation. The second physical change that I can do to the system would be to increase the number of coils in the DC motor. You see, we did with just one coil, right? So what if I, in three-dimensional perspective, what if I increase the number of coils? For example, we were solving the question with just one coil. What if I bring in more number of coils, more number of rotations, more number of turns? So I add more number of turns and then I connect it to the rest of the circuit. This is what they do in our fans, and this is what they do in electric motors. That's why they are extremely powerful even with smaller size, because they have a lot of coils inside of them. So they have implemented all of these factors in real life so that we can get more turning effect. So increasing the number of coils, of course, increases the number of conductors, hence increases the number of force, rotating force experienced by the system. The third thing that we can do is place an iron core at the center of the coil. Now, placing an iron core, what that does is that we did discuss this a while ago, that, for example, this is my north pole and this is my south pole. These are my two loops. Okay, so this one wire is going away, one wire is coming towards me in terms of the current carrying capacity. So if I place an iron core at the center, across which this wire will be looped, right? So what happens is that the external magnetic field, instead of just moving from north to south in open air, now prefers to pass through the iron core, the magnetic shielding effect, right? So they prefer to pass through the iron core. And the good thing about this would be, or the benefit of this would be, that we have, just let me just clear this out. What we have is a coil that is wound around this iron core many, many times over. So now maximum magnetic field lines of the permanent magnet that is placed on the outside will be cut. They will be cut more easily. And hence, of course, eventually increasing the turning effect of the motor. So these are the things that we can do with a DC motor to increase its turning effect, increase its power or rotating power, right? And that is how a DC motor works. Do we understand how it works?